Alright, so now we'll test the remaining methods. We first said we're going to remove the root, so let's do that. Let's comment this out. And here we'll say tree dot remove element. What's the root? We said it was 11, so we'll type 11 here, and then after here we'll remove middle node to try to get that last part of that method. So here we'll set a breakpoint there. We'll step in. First we'll click the debugger. We'll start that, and then we'll step in after. So let's check our root. It says we have 11 left and 20 right, so that's fine. We'll step in. So we're at remove element. We know that part. We know that part. We'll set parent to point to null. So here, if target element, which is 11, dot equals root dot element, which is also 11. So that's true. Result points to root dot element. So temp points to replacement root. We'll step in. We've already done this, but we'll step in. I think we were trying to get here. We'll skip. So now we're here. We haven't seen this part. So we'll say current points to node dot right. Parent points to node. So current points to node dot right. Right child, and then parent points to the node. Then we'll say, well, current dot left is not equal to null, so where does current point to? So again, we're gonna replace the root with the in order successor. That's the next highest element. So we'll say current points to 20 and parent points to 11. So while current dot left does not equal to null, which is true, parent points to current points to current dot left. Okay, so it's trying to find the next highest value. Therefore, where's our tree here? So we're trying to remove 11. What do we have here? 30. So the reason why it's traversing these down this way, pretend if there's elements down this way, is because, okay, we're going to take the next highest element. So how do we find the next highest element? It's telling us we take the right subtree of the root. Then this isn't the next highest element because this is actually closer to 11. So our goal is to find 11 or 12, right? Or anything less than 20, because 20 would mess up our tree if we switch 20 here. Well, it could, depending on the elements, but in this case it might work. If we put it might work if we have if we put 18 here, right? Yeah, so if we switch if we switch 20 into the root, and then 18 goes where 20 is, that may work, but that may not be consistent with a pattern that works for all the elements. So what they're saying is what always works is that we keep traversing down the right subtree until we find, 17, 16, pretend we have 17, 16, 15, 14, 13, 12, and that would be the next highest element after 11. So that's why it does that, and that's why it doesn't traverse to the right. So I hope that makes sense. So while current dot left does not equal to null, current dot left does not equal to null while current is 18. So what's we have under 18 nothing, it does equal to null. So we'll say where are we at now? Here, where'd we go? Link binary, no. So while current dot left, so while current left child is not equal to null, well that's false because it does equal to null. So we're going to skip to here. Current dot left points to node dot left. Current dot left points to where's current dot left? Current, let's remove all these watches. So current dot left points to node dot left. So 4. So it's saying, okay, we're going to swap 11 with 4. So current dot left points to, what's current dot left? Sorry, what's current? Current is 18, so it's going to say, okay, we're going to put 4 under 18, because we're trying to remove 11, correct? So we're trying to remove 11, and then we're going to switch 18, where do we put that? So we're going to perform a traversal here. This is their version of a tree traversal. You can do it different ways. This is the way they're doing it, so they're going to say, okay, well, current dot left, 18's left child, which is null, is now going to point to 4. If node, which is 11 dot right, does not equal to current, which is 18. So as long as 18's not in the spot, it's saying. So our node is where is it? 11. So our nodes are root, right? We're trying to remove the root. So while node's right child, which is 20, does not equal to 18, or it's not the node pointing to 18. Then parent dot left points to current dot right, so parent is 20. So parent dot left points to current dot right, which is null. So parent, let's see, 20 dot left. So we're going to nullify that 18. So parent dot left points to current dot right, and again you can shift the tree any way that actually works. That's what I did technically. You can use the init orders. We're going to do some traversals with a set way. we're going to show you a method. I think this is just a way just that they think that works, but anything, like basically you can use anything that just works. You can shift the nodes around and balance the tree however you want to, as long as it's still the tree still is balanced. So if it's unbalanced, you can balance it, right? So some of these are unnecessary as well. But we'll be going over proper traversals. Or sorry, not traversals, I meant rotations in the next video, so don't worry about that. So here we're just going to say parent.left points to current.right, so parent, which is 20.left, which is 20.left, so 20's left is going to get set to current.right, which is null. So we can do the final tree at the end just to see how it differs. So don't get too worried if you're like, oh well, I don't know why they're doing this. There's different ways to do it. This is just their way. When there's some special ways that just picks the in-order successor and shifts it around. I'll show you the easy trick in the next video, so don't even worry about that. If you're like, well, why are they doing this? You just need something that works. You can shift the numbers any way you want as long as it's balanced. Unless they're like data points which you don't want to shift, that's a different story. It just is, this is a binary search tree, so we're just searching for numbers. It's not like we're storing special numbers. If you are, usually use a heap. But again, this is just an example of a number tree. It's nothing like, it's just show you how to move stuff around. You can store anything you want in here, objects, whatever, and again you can shift them however you want. But to shift a binary search tree which just stores numbers like this, which it has an order like less than 11 or greater than, and the next node's less than or greater than, you can basically set the nodes however you want if you're shifting. So if you're taking the root out, then you can shift them however you want. So this is just a way that they're doing it, and I'll show you some special ways to do it that works every time after. So here we'll just say parent.left points to current.right, so that should get set to null right there. Current.right, which is null, points to node.right. So current dot what's current again? Current is 20. So don't worry, we'll do that. We'll say result points to current and return result. So we'll say that if temp equals to null, root equals to null. So temp was not null. Temp points to 18. Root.element points to temp.element. So temp is what we're going to change, right? So we did all that replacement just to check which node we're going to replace it with. So root.element, which is 11, gets set to 18, so we're going to put 18 now at the top. Was it 18? We could have used, actually yeah, it is 18. That's good, because that's what we wanted. As we said, we want to find the next element in order, the in order successor. Root.set right to temp.right. It's temp. We didn't need that replacement method. We could have just did it ourselves. And I've done a tree where we just rotate stuff, so I'll show you that after. But we're saying okay. Root.set right. So root.element gets shifted to temp.element. So, and then we'll set the root, which is now 18, I think. Set its right child to temp.right, which is 20. It was already like that. And root.set left to temp.left to 4. And now we'll have a look at our new tree. So I'll go to main. We'll say, okay, well the new tree is, what do? They put 18 as the root. Then we took 4 as our left child. So the stats part stays the same. So when you connect, when you set right, then if we were removing 11, 18 would go here, maybe. Yeah, 18 would go here. And perhaps it would be unbalanced then. But it actually would still be balanced. But we'll see how they did it. Again, like I said, there's many ways to do it. Honestly, this is just for testing. Like, unless you're storing your own objects for an app or something, you probably get tested on this in a university level computer science class. And honestly, you can shift them around the way you want, as long as the result is a binary tree. So let's see what they did. We'll say, okay, here the root's 18 now. Left is 4. Right is 20. Yeah, so root is, let's remove that root. 18, left is 4, right is 20. Okay, what's on the left? 2 and 5. Null and null, so that stays the same. And well, what's going to be here? We'll see. So left is null and right is 30. So it seems like that is appropriate. They did it. They did use special methods like before when they nullified it. They set it to like, oh well, that's temp.right and that's temp.left. But you really can put in here is just null. Right? That works. Either way works, honestly. Either way works. Like I said, there's many ways to do it. This is probably what your professor your professor will be looking for. Is like, okay, how can we shift these nodes around, make the tree work, and keep it a binary tree? Is there any possibilities that probably was? We want to get 18 shifted to the root. Is there anything we could switch here? No, because I think this is balanced. I forgot the exact definition, but I think it is balanced because all leaves are within one level of each other. I'm not sure if it's full or complete. I'll have to look at those. We'll do those after. But it does look right. And I think at this point we've really gone through most of the general stuff. So I hope you understand that. And don't worry, we'll be doing some traversals. If you don't understand that, we'll be doing some more practice on traversals with an actual set way, which works on several different trees. So we'll do that. An easier way too, just in a few lines. So we did remove, we did replacement, we ended up getting through the parts we wanted to get, so we don't need to do the middle node. Remove all occurrences. I mean, it's nothing too complicated. I think you can walk through. These are especially easy. There's nothing too hard about those. So I think I'm going to leave it with you there. I think we're past 6 hours, so I mean, it's not too hard. You can walk through it like I showed you how. And once again, if this video did help you, if you'd like to see more free content, free coding, educational videos, and or trading videos, investing, technical analysis, algorithm analysis for trading, financial markets and stuff, you can subscribe if you want to. And the more subscriptions I get, I will be motivated to make more free stuff. So I will be doing the traversals next and the heap. So I'll see you guys there. Take care. Thanks for watching.